Chapter 3, Part 1, Acids, Bases, pK, and Equilibrium. Let's talk about Bronsted-Lowry acids and bases. A Bronsted-Lowry acid and base pair is going to be all about the transfer of protons. A Bronsted-Lowry acid donates or loses a proton, which is H+, and is also equivalent to the nuclear particle. A Bronsted-Lowry base accepts or steals a proton. So let's take water and hydrochloric acid, for example. Water is going to be more basic than hydrochloric acid. Hydrochloric acid is called hydrochloric acid and is also one of our strong acids. So it is going to be a proton donor, and water will be a proton acceptor. So the electrons on the oxygen on water will go to pick up the proton off of hydrochloric acid, which causes the bond between the hydrogen and the chlorine to break. This gives us our products, which are hydronium and chloride, which would be our conjugate acid and our conjugate base. So notice that the acid turns into the conjugate base. It is one proton less than the acid. And our original base turns into the conjugate acid because this is the protonated form of our base. We can also look at this example of acetic acid and ammonia. Acetic acid, again, we have an acidic proton, and ammonia is going to be basic. The electron pair on nitrogen is going to be our vehicle for stealing a proton from acetic acid. So the electrons on nitrogen pick up the proton and break the bond between hydrogen and oxygen. So we have acetic acid, ammonia, and then our products are acetate and ammonium. And I want you to notice also in this flow of the arrows that the arrows are always moving from an area of electron density to an area that is lacking electron density. So remember, there is a dipole here, so there's a partial positive on the hydrogen and a partial negative on the chlorine, which is why the oxygen is interested in the proton at all. And that arrow that we drew ends up making up this bond here. So those two electrons are now the bond between the oxygen and the hydrogen. Same when you look at the ammonia and acetic acid. We drew this bond here, and that is now this covalent bond on ammonium. And when we broke the bond, the electrons from the covalent bond were put onto the oxygens. The reason that we have a third pair here is because they came from the covalent bond between the oxygen and the hydrogen. So let's talk about strong acids. Strong acids ionize completely in solution. So our strong acids, which you had to memorize probably in Gen Chem 1, are hydrochloric acid, hydrobromic acid, hydroiodic acid, sulfuric acid, chloric acid, perchloric acid, and nitric acid. Now you'll notice that hydrofluoric acid is not on here with the other halogen acids. And that's because hydrofluoric acid, though it looks like it should be a strong acid, actually is not. And we'll talk about why in a little bit. Okay, let's talk about aqueous solutions of acids and bases. So remember that when you put an acid into water, the strongest acid that can still exist in water is hydronium ion, because if an acid is truly a strong acid, then the water is going to pick up the proton and form hydronium, so the acid will no longer exist. For example, you put hydrochloric acid into water, and you're going to end up with hydronium and chloride and no hydrochloric acid left over. Hydroxide is the strongest base that can exist in water. So if you have a strong base, it's going to be deprotonating the water and it's going to be in equilibrium with the water. So let's look at a reaction. Hydrochloric acid plus sodium hydroxide, we have a strong acid and a strong base, is going to give us a neutral solution of water and salt, sodium chloride. Let's look at the ionic reaction equation. When we break this up into ions, we have H3O plus chloride, because it is an aqueous solution of hydrochloric acid, plus sodium plus hydroxide. When you add those together, you're going to end up with sodium and chloride, which are retained on the other side as sodium and chloride because it's an aqueous solution. And you're going to have the hydroxide pick up one of the protons from hydronium. So you end up with 2 equivalents of water. So the sodium and the chloride are spectator ions because they are not part of the chemistry that is occurring in this reaction. So we subtract them out and we can see the net ionic reaction. The net ionic reaction describes the actual chemistry that occurred in this reaction. And what actually happened was hydronium and hydroxide reacted to form 2 equivalents of water, while the sodium and the chloride sat by and watched. So all strong acid, strong base reactions have the same net ionic reaction. So let's talk about Lewis acids and bases. How is this definition different from Bronsted-Lowry? So reminder, Bronsted-Lowry acids and bases are all about the transfer of protons. Lewis acids and bases include Bronsted-Lowry acids and bases, but they also provide a much broader explanation of your general acid-base chemistry. Lewis acids and bases, that definition is going to watch the flow of electrons rather than protons. So the definition of a Lewis acid is that it is an electron pair acceptor. So Lewis acids are electron deficient, while our Lewis bases are electron pair donors. They are electron dense or electron rich. This also includes your Bronsted-Lowry acid-base reactions, and most of our organic reactions involve some sort of Lewis acid-base interaction. So for example, if you react ammonia with hydrochloric acid, there are 2 things happening here, and you can look at it in 2 different ways. Well, there's one thing happening here, and you can look at it in 2 different ways. So ammonia has this lone pair here, and we know that hydrochloric acid, being a strong acid, wants nothing more than to donate its proton. So ammonia takes the proton and is therefore stealing a proton, and hydrochloric acid is donating a proton. That is the Bronsted-Lowry definition. But we can also look at it as ammonia is a Lewis base, and it is donating an electron pair to create a new bond with the proton. The Lewis acid, which is specifically the proton here, is accepting that pair of electrons. So this bond that's made here is done through a Lewis acid, Lewis base donation and acceptance of electrons. Now, the reason that the Lewis acid base definition is so important is that this also includes situations where proton transfer is not involved. For example, the reaction of ammonia with aluminum trichloride. Ammonia is, again, basic. It has this lone pair here. Aluminum trichloride has something interesting happening. There is an electron flow going towards each of the chlorines, which means that each of the chlorines are partially negative, while the aluminum itself is partially positive. So that means that these electrons on the nitrogen of ammonia are going to be very interested in the aluminum. But there's no, kicking out of something else. We're not going to break another bond like we did in hydrochloric acid. What we end up with is this complex, where we have a bond between aluminum and the ammonia, but now aluminum is negative and the nitrogen is now positive, and we still have all 3 of our chlorines. So we've created a Lewis acid, Lewis base complex. So, how do we know what is a strong acid and what is a strong base? Or how do we identify acids and bases when they are compounds that we're not familiar with? And this all comes down to pKa. How do we quantify the strength of an acid? Now, I want you to recall from Gen Chem 2 without panicking, because we're not going to do any math in OChem. We just want to talk about where do these numbers come from and what do they mean. Recall that the reaction constant, the equilibrium constant, is equal to the concentration of the products over the concentration of the reactants. For a Ka, which is the acid dissociation constant, you have the concentration of hydronium times the concentration of the conjugate base over the concentration of the acid. Now, the greater the Ka, the greater the concentrations of hydronium and the conjugate base. So that means that the acid dissociated more if those concentrations are higher. So the greater the Ka, the stronger the acid. But then pKa is the negative log of the Ka. So for a strong acid, the concentration of the conjugate base is much, much, much greater than whatever may remain of the acid itself. So Ka will be very large. It'll be much, much greater than 1. This means that the pKa will be small. So if you have a calculator nearby, it might be worth looking at. Type in a number like 1 million or 1,000, something large but not super crazy, and come up with the negative log of it. And you'll see that the number for the negative log is actually very, very small. So a strong acid is going to have a small pKa, possibly, most likely, a negative pKa. For a weak acid, the concentration of the conjugate base is much, much less than the concentration of the acid, because a weak acid is not going to dissociate. So you're going to have a lot of the acid left over, potentially. This means that Ka will be small, and Ka is probably going to be a decimal, which means pKa will be large. So let's look at the pKa values of some common compounds. So on this list, we have some of our strong acids. We have hydroiodic acid, sulfuric acid. Notice our strong acids have negative pKa's. And then hydronium is at negative 1.74. So anything that has a lower pKa than that is considered a strong acid. And everything that has a pKa higher than negative 1.74 is considered a weak acid. And especially when you start to get onto this end, where they are very, very, very weak acids. And this table also has a list of the conjugate bases. So the conjugate base of hydroiodic acid is iodide. You can also look down here and see that we have the conjugate bases of some organic compounds. It is actually possible to deprotonate something that has a proton that is not very acidic at all. You just have to have a super strong base to do it. It's important to note that on this chart, acid strength is increasing upwards. So our strong acids are at the top and our strong bases are at the bottom. So remember that these are opposites. If something is a strong acid, then its conjugate base is going to be a very weak base. If it's a very weak acid, its conjugate base is going to be a strong base. And this makes a lot of sense because a strong acid wants to give up its proton. So hydroiodic acid, once it has given up its proton to make iodide, is really pleased with itself because it fulfilled its lifelong mission. It is not going to want to take back a proton and go back to the acid. So that means it's not going to be good at being a base. Whereas an alkane, such as ethane, if you manage to deprotonate it, it's going to end up creating a very strong base. Notice it is a very, very weak acid. It's going to be very difficult to remove that proton. So once you have any proton anywhere is going to be taken back by this base, so it can go back to something safer and less reactive. So let's talk about predicting base strength. You can relate the strength of a base to the pK of its conjugate acid. The stronger the acid, the weaker the conjugate base. Now, you can also use pKb to do this, but you're going to be asked to memorize a whole bunch of pK values. And if you know those pK values, then you already have the information you need to determine the base strength, because the more acidic something is, the weaker its base, its conjugate base. So if we were looking at a test question that asked you to arrange chloride, acetate, and hydroxide in order of increasing base strength, what you could do instead is look at their conjugate acids and those pKa's and organize them from strongest acid to weakest acid, because the weakest acid will have the strongest conjugate base, and the strongest acid will have the weakest conjugate base. And you can see that by the pKa's increasing from a lower value to a higher value. Okay, so how do we use this information? Why are these pK values important? There are going to be reactions, specifically when you get to OChem 2, that are very dependent on the strength of the base. If you have a weak base, the reaction might not occur, or it will occur in a way that you don't intend. Some reactions require adding in such a strong base that only one possible conjugate base is formed. And it's really important to be able to actually know what those bases are and what's going to work and what's not going to work. So let's work on this first problem. And the question is to figure out which side of the reaction is going to be favored. So if we have ethanol plus hydroxide, hydroxide is going to end up picking up a proton from ethanol. That's going to cause us to break this bond here, and the electrons get put back onto the oxygen. So we're going to end up with ethoxide and water. So the question is, which side of the equilibrium is favored? Meaning, which one is going to have the greater concentrations? So the line above says that acid-base reactions always favor the formation of the weaker acid. And I want to think about why for a second. Strong acids are highly reactive. They want to give away their proton. So if you do a reaction and your product indicates that you've made a much stronger acid, that's not realistic. An acid that is formed and is strong is always going to go back to something that is less reactive. You're not going to be able to keep something reactive from reacting. So how do we determine which side this is going to rest on? And this is going to depend on the pKa's. So the pKa of ethanol, this proton on ethanol specifically, is 15.9. The pK of water, one proton on water, is 15.7. So when I say the pK of that proton, I mean how easy is it going to be to pull off that proton with a base and create the conjugate base. So on this side, we have an alcohol which has a higher pKa. So that is the weaker acid. So our equilibrium is going to very, very slightly favor the reactant side. Although these pKa's are so close together that if I had to draw an arrow to represent this, I would draw something really, really tiny and say like maybe it kind of favors that side. I would say that overall this is very much an equilibrium between the alcohol and the alkoxide versus water and hydroxide. So let's look at the next one. We have phenol, which is this compound here, plus hydroxide. This reaction is going to go in the same way. Hydroxide is going to pick up the proton. These electrons get put back onto the oxygen, and we end up making phenoxide plus water. Now, we already know the pKa of water. It's 15.7. The pKa of this proton that we pulled off of phenoxide is around 9.89 or 9.95, somewhere around 9.9. So, which side has the weaker acid? That's going to be the product side. The product side has the weaker acid by a lot. So we're looking at a number that is approximately 10 versus approximately 16. And remembering that these values, these pKa values, are on a logarithmic scale, that means that this one is 10 to the 6th less acidic. So for every 1 molecule of phenol, we're going to end up making 10 to the 6th of water. So this side is much more favored. Okay, let's look at the last one. We have an alkyne and we have an amide. I told you earlier that there's a type of compound called amide where it's spelled the same as amide, but it has a long I, and this is it. This specific one is called azonide. So an amide with a long I is a deprotonated amine. So azonide can pick up the terminal proton on this alkyne. Terminal means on the end. And that's going to cause this bond to break and put the electrons onto the carbon. So now we've created a negatively charged carbon, and this type of ion is called an alkanide ion. And we'll also make ammonia. So the question is, which side of the equilibrium is favored? Well, the pKa of the alkyne proton is around 25. The pKa of the proton on ammonia is about 35 to 38. So let's just go with 35. So, which side is favored? Well, in this case, again, the products are going to be favored because we've made a weaker acid that is 10 to the 10th weaker than this acid. So to wrap that up again, in the first one, our products, our reactants were favored. In the second one, our products were favored. And in the third one, our products were favored.